Here's an animation that we looked at the start of the last sub-lecture, where we saw the seasonality and temperature change over Earth's surface. And one of the things that we noted was that the equator has the warmest temperatures. So why is it that the equator is warmest? It has something to do with the sun, and we've mentioned this already in class at some point. It's due to two factors, really. The major one is going to be the angle of incidence of incoming sunlight. So when sunlight hits directly at near Earth's equator, that sunlight is more concentrated over a small area. And as a result, it's going to warm that area up more. Near the poles, sunlight hits, but it has to spread out over a much larger area because it's coming in at what we might say is an oblique angle or a small angle, as opposed to coming in directly overhead. When the sun is not coming in directly overhead, that sunlight has to spread out over a larger area, and so you get much colder temperatures in those zones. A second factor that's also important is the path length through the atmosphere. So as sunlight passes through the atmosphere, some of it is scattered or filtered out by that atmosphere. At the equator, sunlight has to pass through less atmosphere, about that much on this diagram, say. But if we diagram that same distance out up here, we see that the sunlight reaching at the poles actually has to pass through a longer distance in the atmosphere because it's coming in at that oblique angle. And as a result, that sunlight gets filtered out more near Earth's poles than it does at Earth's equator. The sum total of all this is that the angle of incidence of that sunlight is really what's controlling why the equator is so much warmer than the poles. Because the poles almost never, if ever, get direct sunlight, even in the polar summertime, whereas the equator is always close to where you are getting the most direct sunlight at any time of year. Why is summer in the northern hemisphere, winter in the southern hemisphere? If you've never been to the southern hemisphere, this can come as somewhat of a surprise that winter in the southern hemisphere in places like Sydney, Australia, is actually going to be in the months of July and August. That's when the temperatures are coldest in the southern hemisphere, which is opposite what we get in the northern hemisphere. And why is that? Any explanation of our climate and how seasons operate has to be dependent then on the fact, or has to reflect the fact that these temperatures are going to be opposite on opposite sides of the poles. It all comes about because Earth's axis, that imaginary line running through Earth around which it spins, is tilted. And as Earth revolves around the sun, that axis stays in the same orientation, but when it's on one side of the sun, one hemisphere will be tilted towards the sun. And the other is tilted away from the sun. When a hemisphere is tilted towards the sun, it's going to have sunlight during a greater part of the day, and more of that sunlight is going to be directly overhead. When the Earth is on the opposite side, then it reverses, and one hemisphere is tilted away, the other hemisphere is tilted towards. So in this diagram, this would be northern summer and southern winter, whereas this is northern winter and southern summer. The fact that the Earth is sometimes closer and sometimes further away from the sun is actually a very small, almost insignificant part of Earth's seasons. It's all about the axial tilt. That axial tilt is also why the summer has longer hours of daylight, and that's reflected in this diagram, and the winter has shorter hours of daylight because less of the sun, or less of the Earth, is covered in sunlight when your particular hemisphere is in wintertime than when it's in summertime. So seasons are all about axial tilts. We can also notice from this diagram that the seasonal changes seem to be greater in the northern hemisphere. You know, pick out any given point, Knoxville, give or take a little bit, And we can see that the seasonal changes are pretty severe. We go all the way from deep orange to blue in our average temperature there. Whereas places in the southern hemisphere that are at, equivalent latitudes or even higher latitudes change far less. We mark Sydney again, and it gets into, medium orange, dark orange, but then only goes as cool as green on this diagram. So why are those seasonal changes so much greater in the northern hemisphere? It turns out it's because there's more land there. Land surface has a lower heat capacity than ocean. When we see heat capacity, what we mean is for a given amount of heat supplied, how much the temperature is going to change. So water, if you add some heat to it, its temperature changes very little. Land, on the other hand, changes a little bit more its temperature as you add or remove heat from it. When oceans are present, because they can absorb a lot of heat and then they can release a lot of heat when it's colder out, before their temperature stabilizes, oceans tend to be able to buffer heat. So coastal places oftentimes are going to be a little warmer than continental interiors for this reason. In the center of continents, where you're away from the oceans, your oceans cannot buffer heat. So this is what contributes to a big difference in between places that are a little closer to the shoreline, like Paris, a few hundred kilometers at most away, versus Winnipeg, right, which is in the center of Canada, away from any ocean. And if you look at the average winter temperatures, they're vastly different, even though these are at the same latitude, the same line of latitude, how far north or south on the globe you are. This lack of oceanic buffering is also then why you get big changes in the seasons in the northern hemisphere and much smaller changes in the southern hemisphere. Not only that, but the continent of Europe is especially warm compared to other places at its latitude during the wintertime. Still see plenty of areas that are green to yellow, whereas other places at an equivalent latitude are dark blue to even purple on this diagram. So why is it that Europe is especially warm in the wintertime? Well, we mentioned one reason already, oceanic buffering. There's a lot of water surrounding the continent of Europe. But there's a particular current that we might call the Gulf Stream or the North Atlantic Current that brings warm water from the Gulf of Mexico through the North Atlantic and brings it nearer to Europe. And as it reaches Europe, it's going to release a lot of that heat. You can actually see that current if you map the surface of the ocean, which is pretty crazy, that there's so much water piling up in this current that it can be half a meter or so, or even more in some cases, above the average sea surface. And that's driven a lot by winds, but also by the fact that the ocean water up here is actually sinking as a result of part of it freezing out. We won't talk too much about the details yet, but we might get into that a little bit later. The moral of the story is that there's a current of warm water that brings heat up north towards Europe. And that's why Europe tends to be a little bit warmer during the wintertime than a lot of other places at its latitude. Let's bring up Hadley cells again. So we've talked about these in the deserts lecture as well, but I want to mention that Hadley cells are these global belts of rising and falling air, and they control global precipitation patterns. And those Hadley cells, remember, are driven by the fact that solar energy is directly overhead at the equator, and it causes air to rise, and that moist air, because it's near the equator and it's absorbing, it allows a lot of evaporation there because it's so warm. That warm air will eventually rise, and as it rises, it cools and forms these big thunderstorms, big thunderhead clouds that rain a lot of that moisture out. That dry air then can move to approximately 30 degrees north and south latitude where it sinks. There's no rain that's going to go on here because that air is already dry. Those big belts of rising and falling air have big influences on precipitation patterns on Earth's surface and make it so that the equator tends to be much wetter and the subtropics tend, not always, but tend to be much drier. You can see one big example here in the American South. But if we look on a global scale, we can see that the South is an outlier, that the American Southwest, that the Sahara, that the rest of the Middle East into Iran and Pakistan, that 30 degrees south, part of South America, part of the southwestern coast of Africa, and then interior Australia. These are all very dry areas. So the American South, to some extent, Southeast Asia as well, are sort of exceptions to this rule. But those big bands of desert tend to explain the wet equator and the deserts that tend to exist at 30 degrees north and south. We've also discussed orographic lifting, which is the process by which mountains cause it to be rainy on their windward side, so the direction that the wind is coming from, and these arrows indicate the wind, and dry on the leeward side. On the windward side, that moist air can rise as it's pushing up over the mountain, and as it rises, it cools, which causes condensation and ultimately precipitation. The moisture in the air rains out, and then as that air descends again and heats up, it's going to be dry. And as a result, the leeward side tends to form deserts. And we can see those deserts forming on the leeward side. This is the direction of wind. So there are big mountain belts here and here. In between those mountains, especially on the leeward side, are areas where it's much drier than on the windward side. So when we think of the Pacific Northwest as being very wet, that's really only the coastal Pacific Northwest. As you get into the interior of those states, it becomes much drier. Those are Earth's current climates, but we should also think about what Earth's current climates are in the context of recent climates, say over the past few million years. And so that's what we have in this diagram here. Two sets of diagrams, or three really. One that goes back 5 million years. That's the Pliocene and the Pleistocene periods in Earth's history. This one is condensed and is only the last 800,000 years, allowing us to see some cyclicity to these climate cycles. Big cycles of up and down with some, smaller zigzags intermediate. And then we can also back up and look over the past 550 million years on the big climate swings that have happened over Earth's entire history. If we want to contextualize Earth's current climate, global average temperature over geologic time over the past 550 million years, we are in the warm phase of a long cold period. The current temperatures are some of the lowest, at least over the past several million years that we've experienced. But our current temperature is probably a little warmer than that minimum, which means that we are in a warm phase, an interglacial, of a long cold period, a glaciation or ice age. Earth has at many times in Earth's history, here or like here or like here, been totally ice-free, we think, at the surface. The fact that we have big ice caps in Greenland and Antarctica are somewhat unusual over Earth's history. So that's something that we want to note, that our climate today, we're used to having ice, but that ice has not always been around, and that there have been times in Earth's history when we're pretty sure it just about all melted. Let's look at the past 800,000 years and see what I mean by this warm phase of a long cold period. So we're in this sort of cold zone and have been descending, and our sort of average temperature has gone down over the past few million years, right around when the Greenland ice sheet started to form about here. During those last few million years, we can see a lot of oscillations up and down, cycles in Earth's global climate. It's not like this happens on a super regular schedule. There's some variation to it, but we can see this sort of zigzag seesaw pattern going up and down, and our current climate is here. Warmer than it was during the last ice age, certainly. So we're in a warm phase of this relatively cold period in Earth's history, this ice age. What causes that zigzag that we were looking at between the warmer interglacials, like right now, and the colder glacial periods when we had ice sheets reaching as far south as New Jersey and Indiana? The largest driving force to those changes are actually these oscillations, so back and forth changes in Earth's orbit. We call those changes in Earth's orbit Milankovitch cycles. Earth's orbit is not perfectly circular. Moreover, Earth's orbit actually changes slightly over time as the sun precesses around its center and as the position of other planets precess a little bit. The forces on Earth are not perfectly balanced to keep it in that circular orbit, and as a result, its orbit can change. And those changes happen on tens to hundreds of thousands of year timescales, which we call Milankovitch cycle after the first scientists that characterized them and described their significance in terms of Earth's climate. We can break them up into three: eccentricity, obliquity or tilt, and precession. We'll talk a little bit about what each of those is. So when we talk about the eccentricity of an orbit, we're talking about how non-circular it is. And these diagrams are pretty exaggerated, but a low eccentricity orbit would be one that looks close-ish to a circular orbit, so that it's always about the same distance from the sun. Whereas a high eccentricity orbit is one in which there are periods when it is very far from the sun and periods when it is very close. Once again, this diagram is really exaggerated. It's not going to be that we're 3 times closer to the sun at some points than others when our orbit is the most eccentric, but it might account for a few million kilometers out of our 150 million kilometer radius on average orbit. And these can have some effect on Earth's climate. The tilt or obliquity is another cycle that can change, where Earth's axis right now is tilted, I believe, at about 23 degrees. But that tilt can change between about 21.5 to 24.5 degrees. And so that's going to change sort of the magnitude of the difference between winter and summer. So that's a big change that can happen on Earth's climate as well. The last one is going to be precession of Earth's axis, which is sort of how it wobbles over time. So, right now its axis might be pointing this way, but over time it might be changing to point this way at this point in Earth's orbit. Kind of like how if you watch a top spin on the ground, it's always spinning around its axis, but that axis can change orientation as the top wobbles around and ends up pointing this way to that way until it finally falls over. Earth is not going to fall over as a result of precessing because there's no friction against anything, but it can precess, its axis can change orientation over time, which does have some influence on seasonality, right? And so that's going to influence climate as well. We can see these Milankovitch cycles combined here into a big stack of this is the final influence here of all of those Milankovitch cycles. When the northern hemisphere summer is cold, that means that the snow that has fallen in the winter doesn't all melt. And that is what allows ice sheets to grow. There ends up being what we will call a feedback, and we can discuss what that means a little later, where as an ice sheet grows, it can reflect more and more sunlight because ice sheets are fairly bright in color. As a result, it gets even cooler. It allows the ice sheet to grow even more, which allows it to get even cooler. So the Milankovitch cycles are really just the little kick that we get to start the warming or cooling that can allow the ice sheets to grow substantially or shrink substantially based on other feedbacks that are going on.